Hello everybody, this is the course presentation for E6895 Advanced Big Data Analysis, and our topic is autonomous learning from text to vision. I'm Sun Mao and my teammate is Luo Xinchen. And let's quick overview what our topic about. It is a system that makes the machine to learn just like human beings, and you can regard it as some kind of distilling knowledge from some raw data. And ideally, when we feed the system with some raw image with text, the system can understand all the mapping relations. And later on, when we feed it with some more pictures, some new pictures, it can tell us what kind of information this image is trying to convey. Or when we give the system some text, it can help us to find some relation, the related cluster of pictures. And if we feed the system with some video, it can draw the bounding box for us and find out the clusters it belongs to. Let's see how the system works. First, we have some raw data, that is the videos with closed captions. We divide it into two parts, the image and the captions. In the image, we first do the segmentation to get some like bounding box, and then we cropped the image according to the bounding box we predict, and then we do the transfer learning to extract the representation of the bounding box picture. And when we have the bounding box picture representation, we cluster them use the k-means into different clusters. In our example, we cluster into 85 different clusters. And in the caption part, we use some topic model to get the some representation of the text. And also we use the word representation. That is, you use some external text to train a system which can represent our original word into some word vectors. And when we have these word vectors along with the topic model we have, we can infer some the label of the descriptions. And when we have the clusters and the label of each picture, we can do some like voting process to get the results. That is, which picture should belongs to which cluster, such result. And this is just some details. We can skip them. And it's a summary of the previous work. And in our final project, rather than just write the model ourselves like before, we implement some state-of-the-art model, that is the YOLO, which is regarded as really fast and useful in like dealing with the videos. And also in the caption part, in the description part, we implement the global vector for word representation. It is a better word representation method to gauge the label distributions. And also now with help with YOLO, we have the multi-object image, and we can get the bounding box of the multi-object image and use the probability model to predict the label for each image. Also, we attempt to implement our method to predict object occurring in the videos, and you can see some of the demos in our link later. Let's quick overview some of the knowledge we use in our project. First is the transfer learning. Transfer learning is some kind of, you can think of as you already have some pre-trained well model with great parameters, and it can help you to build your own model more quickly. And the method is that you have the original model and you load some of the parameter into it, and like you cut some later layers and keep the original ones, and then you add some more layers and do the fine-tuning of the whole model. And it is really useful when you do not have enough data for your training, or you do not have enough running time to train a lot of epics. And also the image localization. The basic idea used in our project is when you have some like representation, the CNN code of your image, and then you map it into 4 different numbers, and this 4 number is represent one bounding box. The bounding the exact some details about that is 2 of the numbers, the first and the second number, represent the coordinate of the central point of your image, and the third one represents the width of your image, and the fourth one represents the height of your image. And when you have the CNN code, you can understand the CNN code at some high level knowledge of your image, like the age. Some of them represent the age, some of them represent the color, such things. And when you have the CNN code, you have the target, which is your bounding box, representation, and then you can do the mapping process throughout some neural network. So the state-of-art method includes the RNN, faster RNN, and this is to the classification problem, and it is really accurate and works quite well, but really time consuming to train and to get the result. So in our model, because we want to like apply it to some videos, we use the YOLO. It is really fast, and because it only look at your original picture once, and it only goes through the CNN code once, CNN process once. So the basic idea behind the YOLO is when you have the CNN code, you predict like 48 different bounding box, and also you predict some kind of the probability that your bounding box do contain some kind of object, and then you set a threshold, and the bounding box with the probability higher than the threshold, you regard it as some kind of, it do have some image, have some object, and then you try to merge this 49 different bounding box. That is, if the intersection between two bounding box is over 40%, you merge these two bounding box into one. So here's some result. You can see the like multi-object are obtained from the YOLO network. And the k-means clustering, whenever you have the representation of the bounding box picture, you can just do the k-means clustering to get different clusters. The basic idea behind k-means is that you have some kind of hyperparameter, which is k, like you want to cluster your image into k different clusters, and then it just do the like keep calculating the distance between each picture to the cluster label that you put into this space, and keep divided into the k different parts. And when he has the first result, it then calculates the central point of the result you already have, and then calculate the distance between the points to this central point that we calculated before, and just keep doing this. You get different clusters. And in the caption part, the main thing we use is word embedding, which is a great way for the word representation. The basic idea behind this is that each word is represented with a vector, and the vector reflects the word representation in some semantic space, the vector space. And we can see some result here that the word that has the similar meaning do like be similar or in some like be near each other. Some of the dataset and tools we use is like the Coco database, the YouTube caption, and tools like the Keras for image representation, scikit-learn for k-means clustering, TensorFlow for word representation, and NLTK for word processing. Now here's the two ways to do the word representation. The first one is you use the central word to predict the word behind it and before it. The second way is you use the word behind it and before it to predict the central word. And this is a two unsupervised way to get the word representation, the word embedding. And whenever we have such kind of word embedding, we calculate between the words and labels. That is, you already have such labels like L, I, and you calculate the distance from each of the word in your description to this kind of label. And this is like the correlationship between your word, the label given your description. This is description of your word. This is just an example. A bicycle is in front of a building, and just calculate the correlationship here, and we can see the picture is this. So here's when we do the clustering. It is some kind of clustering from here. You can just use the average of each word representation in these clusters to do the voting process. Then whenever we have the label we predict from the word, and the label we cluster in according to the image, we this is two distribution, and we put some weights in it, like we put the alpha to the word label, and we put 1 minus alpha to the the cluster prediction. Then we can get the label. So here's another example, like the caption is a kitty sticking its head outside a coffee cup, and the label distribution is below that, like the cup, the cat, the book. And we do the multi-object inference, like we first have the bounding box of these two, and this image will cluster into will have such label cluster distribution, like the cat is 0.5, the sheep is 0.1, and obviously we can predict it is the cat in here, and this is the same. So you can see some of the result in our video demo in our in YouTube, and we provide the link here. So here's just we extract some of the pictures from our video. This is the picture from just using the original YOLO, some supervised ways, and the right one is the result from our project. Like we can see here, the bounding box are same because they both based on the YOLO. In the first picture, which is from the YOLO prediction, it predicts the bird as dog, but our project predicts as bird. And also you can see some later on that this one is predicted as bird, but ours but this time this is right, but before it is wrong, but ours always predict as bird. This is kind of because that we use the label distribution from the text and the pictures, like we combine these two things together, so the prediction should be more smooth, like it always is bird. Some other example, like our model predicts this as a floor because it has a floor details for the pro features, but here maybe the supervised model has done too much overfitting or something. It just predict as a wine. Here's just some other examples. You can refer to our video for details, and this is the result. The word vect transport learning is here, and also some other models. You can see the result here. Actually, it's quite good, but we can see before that they do contain some limitations, like the overlap among objects cause errors. Because you can see the pictures, sometimes it kind of confused because it predict too much bounding box. And the text part, the distribution is generated based on the independence assumptions. We might improve it using some more complicated language models. And the mapping process now is based on the independent assumptions. We can further implement some like the weighted scoring system using the two distributions from the text and division and optimizing them together to get some better results. Here is just some reference. Thank you.